Hello, everyone. I hope you're all doing well. I miss y'all and know you are so close to finishing your school year, so finish strong. And so in this video, we're going to be doing the third lesson in your admin for pre-cal. It is called Inverse Trigonometric Functions Tutorial. So as you go through this video, just keep in mind that you can pause it, take breaks, and also I would always try to pause it and try to do a problem on your own and then play the video and see if you did it correct. That's the best way to learn the material. And then if you have any questions as you finish this video, please reach out to me and let me know. So here's the first video. It's their introduction, admintum. We don't need that. Here's the title. Slide 3 is our objective. We're going to learn about inverse trig functions. Introduction video, you can watch that on your own if you want to pause the video and watch that. And so in this introduction page on slide 5, they talk about a problem where they're trying to find an angle. So keep in mind, when we do inverse trig functions, you are solving for an angle value. It kind of goes back to what we've been doing on these different tutorials where I say, okay, where on the unit circle you look for a certain value and you say, okay, what angle gives us that value? That's the concept that we're going to be learning. It's just learning new notation on how to write that out. So you can read this. It does come back to this problem, but I'll talk about it when we get there. But that problem I don't like, and maybe some of y'all can correct me when we get there. Please let me know. But I'm not going to take the time to read that because we're actually not even going to do this problem. We're going to do another one. So this slide 6 is just reviewing inverse functions. So if you read this, it says, recall that if you know one of the acute angles in a right triangle, you can find the ratio of the length of one side to the length of the other. You've been using trig functions, all your trig functions, to answer those problems, right? We know sine of 40 degrees equals opposite over hypotenuse. So I had to think for a second of whatever, using whatever triangle they give you. So that's what that's talking about, using SOHCAHTOA. But what happens if you know the side lengths? Could we use those two side lengths to find the angle? So now, in the past, we've been looking for either like an ordered pair value or a side length of a triangle. Now we're going to use the ordered pair value or the side lengths of a triangle to find the angle. So this is where the power of inverse trig functions comes into play. From earlier lessons, our functions, you know, as a one-to-one function, you have an inverse. So this is just going back to what we learned about inverse in the first semester. I think it was in Unit 3. And these are some important things to remember. So a function f of x has an inverse if and only if it's one-to-one. So how do we test, what does one-to-one mean? Every x value has one y value and every y value has one x value. So the way you test that is we do a vertical line test to make sure that the original is a function, and then we do a horizontal line test to make sure that the inverse will also be a function. And then these next two bullet points are just saying the range and domain switch, right, for a function and its inverse. And then lastly, if you plug an inverse function into the original, you should just be left with the variable. This says y, but it could be x or whatever. I don't think we'll use that fact, but you should remember that from Unit 3. So it says one important feature of trig functions is that they are periodic. Therefore, each range value can be associated with an infinite number of domain values, right? Because your unit circle goes around and around and around. So when you graph it, the wave goes forever. So it says, for example, if cosine of 0 equals 1, right here at the top, well, this is sine graph. Why did they talk about? Skip the cosine part. It's the same with sine. Sine of 0 is 0, but then also sine of pi is 0, sine of 2 pi, sine of 3 pi, forever. There's more than one x value for every y value. So according to our definition, a function must be one-to-one. This is not one-to-one because it would fail that horizontal line test. If you draw a horizontal line across this sine graph, it's going to cross it more than once. So how can we even begin to talk about their inverse functions, it says? Well, what we can do is restrict the domain to have a set of points so the function is one-to-one. So it does pass the horizontal line test. So then down here it says, let's take a closer look at how this works using the sine function as an example. As you can see, the graph of the sine function, we will restrict the domain to just be negative pi over 2 to pi over 2. And the restricted function does in fact pass the horizontal line test. So what they're saying is, okay, what piece of this graph could we just take to where it'll pass the horizontal? So you want to take the most like middle piece. So they decided to go from negative pi over 2 to pi over 2. As soon as you go past pi over 2, now you would fail the horizontal line test. So we don't go past that. Is that the only option? No, that's just the domain that they tell you to use, basically. You could restrict it in other places, but we're going to go with negative pi over 2 to pi over 2. So when you use your inverse function, you're only going to talk about from negative pi over 2 to pi over 2. So slide 8 says, which domain restriction would allow you to define its inverse of a tangent function? So I thought it might be helpful if we have the tangent graph. This is what the tangent graph looks like, if you remember. So does this pass the horizontal line test? No, right? Because if you draw a horizontal line, it crosses it more than once. So what piece could we take to where it does pass the horizontal line test? So think about that on your own. And then if you think about it, well, just one of these cubic looking pieces would pass the horizontal line test, right? If we just took that middle, I'm using my hands like y'all can see what I'm covering up, but we just take this middle piece from negative pi over 2 to pi over 2, that would pass the horizontal line test. It would only cross the horizontal line once. So we're going to actually use that same restricted domain for tangent from negative pi over 2 to pi over 2 and just ignore all the repeats. So it's actually going to be the same answer as sine. Okay, in this slide, it starts to talk about, okay, so how do we actually evaluate then? So it says, now that we have a restricted domain for the sine function, let's define its inverse. The inverse sine function, which is represented by either sine with a little -1. Now, it says note that sine -1, that's not math, right? When you're doing inverse, that's just notation. It doesn't mean you're actually like raising it to the power of -1. It's just how we note that it's the inverse of sine. Now, because that can be kind of confusing, they say that you can also use arc sine, okay, ARCSIN. That's the exact same thing. It's just two ways of writing the inverse of sine. So both of those are defined as the inverse of the restricted sine function where the domain is now negative pi over 2 to pi over 2, which that was the restricted domain for the original. So just keep that in mind. So now when you go, now this just talks about it can be written either way and what's the advantage of both. Don't worry about that. Just know they're the exact same thing. So then right here after the parentheses, it says y equals sine -1x, or the inverse of sine, is also equal to sine y of x, right? Because you switch your x and y. Where now, instead of that being the domain, that's the range. And your original range is now your domain, -1 to 1. To summarize, the inverse sine of x is a number or an angle, that's what I would say, between negative pi over 2 and pi over 2, whose sine value is whatever x value they give you. So here's two examples. Find the value of inverse sine of 1/2. So you could click on that and read it. I think I pulled it up on my own. So to keep, this is what I was reading in that paragraph. So originally we have y equals sine of x, and x is your angle, right? And oops. And y is the value from the ordered pair, which is, since it's sine, it'd be y value, or if it was tangent, it'd be y over x value. But now that it's inverse, that switches. So now the x value inside your inverse sine is the value, and your y value is an angle. Those roles switch letters. So for example, originally if I'd given you sine of pi over 6, well, you would say, okay, I'm going to go to my unit circle, pi over 6, sine is the y value, the answer is 1/2. Okay, but now it's just opposite. Now they're giving you the 1/2, and they're saying, okay, what angle has that y value of 1/2 since it's sine? And so theoretically, you would look on this whole unit circle and you say, okay, y value of 1/2, it's here at pi over 6, and it's also here at 5 pi over 6. You can't have more than one answer for inverse. So that's why they restrict it. If you're doing an inverse problem, you only look in the from negative pi over 2 to pi over 2, which let's think about this. Positive pi over 2 is the first quadrant. If we go to negative pi over 2, that means you're starting at 0, and negative means you go down. And pi over 2 is one quadrant. So negative pi over 2 is starting here, going down through this fourth quadrant. Positive pi over 2 is going through the first quadrant. So the way I think about it is my domain restriction means when I'm looking for an inverse value of sine, I'm only looking in quadrant 1 or quadrant 4. So that means I'm not even going to look over here. So that 5 pi over 6 isn't even an answer. I only want the what was the problem? I only want the sine value of 1/2 in the first or fourth quadrant. Okay, that's always the same. That's never changing for inverse problems, for sine at least. It's first and fourth quadrant always. So this slide right here would be a great thing to write down or take note of. We'll talk more about cosine and tangent in a second and about this quadrant 4 information. So all that to say, it's just switched. Now your answer is the angle that gives you that value. So the answer is pi over 6. Same thing here. You would say, okay, now that it's arc sine, exact same problem, you're going to say, okay, what angle gives me a sine value of 1? So you go to your unit circle. In quadrant 1 and 4, you look for a y value of 1, which would be right here at pi over 2 or 90 degrees. So let's see if that's what they give us. Yes, y equals pi over 2. Hopefully this is starting to make sense on the goal. So here they talk about cosine. And they said, now let's look at the inverse of cosine function. As shown in the graph, this would not pass the horizontal line test, so we're going to restrict the domain again. Now, you can't do negative pi over 2 to pi over 2, because if you did, you would fail this horizontal line test, right? It would cross a horizontal line twice if we use that same domain. So now we're going to pick a new domain. So for cosine, they pick 0 to pi. As soon as you go back up after pi, you would fail the horizontal line test. So they go just 0 to pi. And that's all it's really saying. So now you do the same idea. Let's see if I put this on here or not. No, I did not. So if I want to know the inverse cosine of -1, well, I ask myself, okay, what unit on the unit, what angle on the unit circle between 0 and pi have a cosine value of -1? So let's think about this. If I'm on my unit circle and I go from 0 to pi, so no negative angles, so I don't have to worry about going backwards. 0 to pi is just the first 2 quadrants. So that's why I put here cosine's restriction 0 to pi, or you could think about it as quadrant 1 and quadrant 2. So what angle from quadrant 1 to quadrant 2 has an x value of, what was it, -1? Yes. Well, that would be right here at pi. Okay, so these restrictions, anytime you're doing inverse sine, you're going to look at quadrant 1 and quadrant 4. Anytime you're looking at cosine, you're going to look at quadrant 1 and quadrant 2. Anytime you're looking at tangent, you're going to look for in quadrant 1 and quadrant 4. Okay, that's never going to change. And here they talk about tangent, which we already did. We already talked about this, but so let's just do this problem they have here. It says, what's the value of inverse tangent of 1? So you're going to say, okay, in quadrant 1 or quadrant 4, what angle has a tangent value of 1? So we know tangent is y over x. So you're going to go look at these order pairs in this like right side of the unit circle, because that's quadrant 1 and quadrant 4. You're going to say, which one of these ordered pairs would the y value over the x value equal 1? Well, we know if the order pair is the same, when you do y over x equals 1. So right here at pi over 4, this ordered pair, y over x would equal 1. So that's your answer. Why is it not down here? Because we know all these tangent values would be negative in quadrant 4, because it's a negative over a positive. So we knew our answer needed to be in quadrant 1. So it should be pi over 4, which that's what they give you here. So here's just some more practice problems. So this is where if you feel like you understand, I would pause the video and try these on your own, and then you can watch the video and see if you get it right on your own, you can skip ahead, or if you need to watch the video for explanations. So the first question is inverse sine of -1/2. Oh, you know what? I hope you didn't already pause the video because there's something I didn't talk about yet. So I ask myself the question because it's sine, my restrictions is quadrant 1 and 4. So what angle in quadrant 1 or quadrant 4 does sine equal -1/2? So in other words, because it's sine, the y value equal -1/2. So we go to our unit circle and these right side and look for a y value of -1/2, which is here in degrees. Oh, because it asks for degrees, doesn't it? In the instructions, it says it wants it in degrees. So that would be 330 degrees. Now I want you to be careful because if you think about it, 330 degrees is not in your domain, right? Because we went down to get to -π/2. These angles are all like greater, not in this interval from -π. Think about it instead of radians degrees. We went from -90 degrees to +90 degrees. Well, 330 degrees doesn't fall between -90 and +90. So instead of using these positive, because we went down to make this -π/2, we're going to use the negative version for all these angles in quadrant 4. So instead of 330 degrees, we went down 30. So that would be -30 or -45 degrees or -60 degrees. Okay, and if it was in radians, I would go and write down these negative versions. If you have your unit circle on paper, it would be -π/6 for 11π/6, -π/4 for 7π/4, and -π/3 for 5π/3. So you're not going to use any of those positive. If you use quadrant 4 when you're doing sine or tangent, you're going to use the negative version of those angles. I hope that makes sense on why. Ooh. So because it was at 330 degrees, we're going to use -30 degrees because that's the same spot. It just keeps it in our actual domain on that graph. So for radians, it would be -π/6 because it's at 11π/6. So, but since it asks for degrees, excuse me, you would type in, I think if you wanted to, you could use your equation editor or just type in -30 and you don't have to do the degree sign since you're typing it. And that was their answer. Okay, so question 2 says arctangent of √3. So remember, arctangent is just inverse tangent. It's just another way of writing it. So you ask yourself the same question. What angle in quadrant 1 or 4 does tangent equal √3? And we know tangent is y/x. So in other words, where will the y/x equal √3? And then I went ahead and put it over 1 to make it look like a fraction since it's y/x. So we want √3 to be in the y, and we want 1 to be in the x when we simplify it. And think about it, it's positive. So if you're in quadrant 1 or 4, tangent's only positive in quadrant 1. So we don't even need to look at quadrant 4. Just look at your quadrant 1, because these are the positives for tangent. And look for where, if you did y/x, it would be √3 over 1. That would be at π/3 or 60 degrees, right? Because if the over 2's would simplify out, so you'd be left with √3 over 1, which is √3. So the answer is 60 degrees because they want it in degrees. And you don't have to do anything funky there. You only have to do the negative angle thing when you're in quadrant 4. And that was correct. Now, last one is cosine. So cosine is the one with its own restrictions, right? Cosine, you do quadrant 1 and 2. So you're going to ask yourself the question, in what angle in quadrant 1 or 2 does cosine equal 1/2? So in other words, we know cosine is the x value. So where's the x value 1/2? We're going to look at quadrant 1 or 2 for an x value that's 1/2. Well, that would be right here because these x values are negative. So at 60 degrees or pi over 3, which is what I put here. And they want the degrees for this slide, so you're going to put 60. And then you can say how you feel like you did. So here it's just talking about how instead of like using the unit circle, you could think about it in terms of SOHCAHTOA. Sine is opposite over hypotenuse, cosine of an angle equals adjacent over hypotenuse, and tangent of an angle equals opposite over adjacent. So I think we're going to pause on thinking about this till we get to the word problem, because this really is using the unit circle, but we'll come back to this in a second. Okay, so this is the same idea. You're going to ask yourself where on the unit circle, and we know for tangent, we got to use quadrant 1 and 4. Will tangent equal negative square root of 3 over 3? And it says in degrees, and you don't have to do the degree sign. So let's see if I pause it and try it on your own. So we know that it needs to equal negative. So at 330 degrees, which is also negative 30 degrees, the ordered pair is square root of 3 over 2, negative 1/2. So if you find the tangent value there, you would do y over x, which, look, I forgot the negative. My y value was negative 1/2. Oops. So then, since they were both over 2, those simplified out. So then you're left with negative 1 over square root of 3. And then I rationalized it because I had my square root on the bottom. So I multiplied by that square root of 3 on the top and bottom, and it became negative square root of 3 over 3, which is what I started with. So what is my answer is that angle. But don't forget, if you're in quadrant 4 for these inverse problems, you got to use the negative version. So negative 30. Okay, if you type 330, it's going to say it's wrong because that's not technically in the restricted domain. It's the same right spot, but it's not the right angle. It's not the right way to get to that spot. Okay, so here it talks about a calculator, and I know y'all don't have those calculators we use in class. So what you can do is if you go to Google and you just type calculator, I'm sure there's a bunch of different ones you could do online, but Google has a calculator right here. So I'm going to show you how to use this one. But if you have another one online you like to use, or your own actual calculator, that's great too. I think your phone also can do this. So it says, what's the value of arc sine of negative 0.4552? Well, if you want an arc is just inverse, so you would click this inverse button, and you see how it puts a negative 1 on these? And so it said arc sine, so I'm going to click inverse sine, which it types arc sine. So you could probably type it yourself and it would let you do it. And then it wants negative 0.4552. Now, if you look, it wants it in degrees. So your calculator is in degree mode. So I should have changed this. You got to click right here on degree. Make sure it's bolded instead of the radians, the rad. Click equals. And that's your angle answer, negative 27.077, which is what they just rounded it. So you could do these two if you want inverse tangent. You can clear this and do inverse tangent. It's already in degree mode still. And then type what you have in 0.683. And 34.33, which let's see if that's what they got. Yes. And you could do cosine too. Just don't forget you got to click this inverse button every time before you click whatever trig you want to do. So here they have you practicing that. I'm going to have you do that on your own. Hopefully you can do that now that I showed you. So just don't forget whether it's cosine with a negative 1 or it's arc, you're doing the same thing. You're going to click inverse. You're going to click which one you want, put in whatever they have, and then just click equal and type that answer. Once you change this to degree mode, it stays in degree mode. You don't have to do that every time. So pause the video and go ahead and complete that. And make sure if you're having trouble typing it in the calculator, let me know. Okay, so here it's just talking about what are the graphs going to look like. So we know when we want to graph an inverse, what we could do is take the original ordered pairs. So when we graph the original sine function, what did we put on that x-axis? When we unwrapped it on the unit circle, when y'all did that thing with spaghetti, you put the radians on the x-axis, and then the sine value gave you your y. So what's on the y-axis is whatever value you get for that trig. So in sine, it's the y value from the ordered pair. So you get this, you could create a table with those values. And then if you click the arrow, that's the original sine graph. So to get its inverse, you switch the x and y values, right? So if you look, originally the y values were like 0, 1, -1, and the x values were radians. Now our y values are radians, and our x values are those values, 0, -1. And so if you switch those, what you end up getting is this blue graph that's labeled arc sine. And remember, it's restricted, so that's why it just ends, because we're only going from -pi/2 to pi/2. We didn't use the whole sine graph. Now, when you do that same thing with cosine, and you got the original cosine values, and then you switch the x and y, you would end up with this graph. Because remember, it went from 0 to pi, so that's why it's above the x-axis, because we never use negative angles. Because the restricted domain becomes the range on the inverse. So those are what those two graphs look like. And then here they give you the tangent graph, what it would look like. It looks almost like a cube root function. It's like a flat. So they put it all on here, which is kind of a lot. This is talking about how you graph it. So I'll show you on the next slide. Oh, wait, maybe not the next slide. Here it's just comparing them. So I don't know if y'all remember, but we learned this again in Unit 3 when we talked about inverse functions, that a function and its inverse are reflected across that diagonal y = x line. So sine and arc sine, if you folded it diagonally along the line y = x, they would fall on top of each other. So here's a question. It says, which of these graphs represent the inverse cosine or arc cosine, because those are the same, with its restricted domain? So if you just remembered it from the slide, you could pick it. But if you forget about a graph, you can always go to desmos.com and click Start Graphing, and I could graph this. Oh, wait, why don't I see it? I'm going to use their keyboard. Go to Functions, and then they have these inverse functions right here. We're not using the H stuff. We're using this column with the -1, and you put X. And it's this one. Now you could go get your x-axis how you want or the y-axis how you want, but it's the one that's above the x-axis. So which one looked like that? It would be this graph B. And then here it says, recall that we would have to restrict this domain. So we're only using this, because the middle part of tangent just looks like a cubic. So think about what's the inverse of cubic. It was cube root. So the inverse of that restricted domain of tangent is going to look similar to cube root, arctangent. Okay, this is the slide that goes back to that original problem from the beginning. Now I don't agree with this problem. I feel like it's set up, the picture doesn't match the work, and I'll explain to you why. And if you feel like looking at it and seeing if I'm wrong, let me know, but I can't figure this out. So let me know what y'all think, because what this is saying is they're using, so this angle right here is labeled θ/2 in the picture. So if you look at the triangle they made with that angle, they said that the opposite side is d/2. So they're using this triangle right here and d/2, because this whole length is d, and they split it in half just to get this bottom half. So then the adjacent side for that triangle would be this whole length right here. I hope you all can see my mouse. If you can't see my mouse, this isn't going to make any sense, and don't worry about it. But this whole length, and they say that's the adjacent side is f, but f stops right here. That doesn't go all the way to d. So that's why I feel like this is not a good setup. It doesn't match. So we're not going to do this problem. There's other real world problems that we're going to do. But if you look at that and you can see where my thought process is wrong, feel free to let me know. Okay, so this is the one that we're going to look at. Let me see if I have a slide on here before I start. Forget. So this is, I guess, all I said. So we can think about this, now that we're not going to use the unit circle for these real world problems, that originally tangent of theta, which theta is representing an angle. So tangent of an angle equals the opposite side divided by the adjacent side. So now if we switch it to get the inverse tangent or get theta alone, the angle theta equals the inverse tangent of opposite over adjacent. So we can represent an angle value by inverse tangent of whatever ratio it originally is, right? Theta equals inverse tangent of opposite over adjacent because it's TOA. You could also say theta equals inverse cosine of adjacent over hypotenuse, or theta equals inverse sine of opposite over adjacent. Okay, we're going to probably use tangent the most, but we will use sine and cosine. So let's see how they use it for this problem. It says, imagine that you're walking around an art gallery and stop at a painting that you really like. The painting is hung on the wall 8 feet away from you. The painting is 5 feet tall, and the bottom edge is 2 feet above eye level. Determine the viewing angle theta for the painting. So if we see theta is this top angle, and that's not a right triangle for theta. For just this top angle, that's not a right triangle, so you can't really do SOHCAHTOA alone. But what we can do is break it up. So we know if we look at these options, which one's true. Well, theta will be the big angle minus this small angle will equal this leftover theta, right? If we take the big minus one of the small angles, it'll equal the other small angle. So we're going to subtract this called alpha from beta to find theta. That's beta, B-E-T-A. But just think about it. We're going to subtract this smaller angle from the big angle to get what's left over theta. And it shows it down here, the setup. So now if we can find beta and we can find theta, we can subtract them and get our answer. So the next option is how, because all these are talking about solving for alpha, A. Let me just call it A and B so that doesn't get confusing. So let's think about alpha down here. Just think about this lower triangle at the bottom. How would we know alpha? Well, we know the opposite side of this triangle is 2. The adjacent side to A is 8. So we know the opposite and we know the adjacent. So what is that? Opposite and adjacent, that is tangent. So now, because we're looking for A, which is an angle, right? So A, the angle, which is like theta, will equal inverse tangent of its opposite side over its adjacent side. So set up an equation for A in terms of the 2 and 8. This one's wrong because it says use sine, but we don't want to use sine because we're doing opposite and adjacent. This one says cosine, but we don't want to use cosine. So we're going to click the first one. So it sets it up inverse tangent of 2 over 8 because 2 is opposite, 8 is adjacent. Now it says, what could we do next? Set up an equation for B in terms of the 7 and the 8, right? So B is this big whole angle for this big right triangle, the whole picture, which the opposite side would be 7 plus 2. 7 plus 2, 5 plus 2, which is 7, and the adjacent side would be 8. So we don't want to do the, oh wait, here. Set up an equation for B in terms of 7 and 8. We don't want to use cosine because it's opposite and adjacent again. If you're looking at the big triangle, that hasn't changed. This says take the inverse tangent of 2 over 8. You actually could do that. They just want you to do this one, I think. Because now look, so we know alpha in terms of inverse tangent. We know B in terms of inverse tangent. So we're just going to plug those in for B and A to this original setup to get alpha. To get theta. So it says substitute the B and the A into the expression we originally wrote for theta. So now theta was B minus A. So now it's going to be theta equals B was inverse tangent of 7 over 8 minus A was inverse tangent of 2 over 8. And they just typed that in the calculator and got 0.47 radians or 27 degrees. So you would have to use this calculator. You would have to do one, get it as a decimal, do the other, get it as a decimal, and then subtract the 2 decimals. So you'd actually need to write that out step by step. So let's see some more. word problems. This one's very similar. So if you get the concept and the setup, it gets easier because it's always going to be if a leftover angle will equal the big angle minus the small. So the big right angle minus the small right angle will equal this leftover piece that we're looking for. So it says in the 1960s, drive-in movie theaters were very popular. You drove your car into a lot and watched the movie. Ideally, you would want to get a spot that's directly lined up with the screen, but sometimes that's not possible. Imagine you're going to drive-in theater where the screen is 30 feet wide. You're parked perpendicular to the screen, so you're like making a right angle with the screen, but the near edge of the screen is 40 feet from the road. The angle the car makes with the screen can be represented by theta. Here, the equation represents theta. So it's the same setup, right? So theta is this leftover. So they took the big right triangle. This whole right triangle would be set. The opposite side is 70. The adjacent side is whatever this x value is. So 70 over x minus the small right triangle. Remember, you can only do SOHCAHTOA with right triangles. Would be the 40, would be the opposite, and the x would still be the adjacent. So if you subtract those two values, you should get whatever this theta is, where x represents this adjacent side, basically. So it's saying, suppose you're parked 100 feet away, then that makes your x 100. So they replaced x with 100 for both equations. And then you just type that in a calculator. You'd have to do it step by step, get both values, and then subtract them, and you'd get 18.29 degrees. So same setup, just another problem. Here's some problems. I think this is the last slide where we actually do something. So I think I have these on my PowerPoint. Let's go ahead and read the first question and we'll see. It says an airplane is flying at an altitude of 6 miles toward a point directly above where you're standing. If you're standing X miles away from the spot that is perpendicular to the plane, what's the equation that relates to the angle theta as a function of X? Then use the equation, solve for theta when X is 2 miles. So first it's just keeping this adjacent side X, and then they replace the X with 2. So here's our theta. They're saying, how could you define theta? Well, we know if we're looking for an angle, then we're going to use inverse. Well, we want inverse what? Well, we know the opposite is 6. We know the adjacent is x. And opposite of adjacent is tangent. So we would want to pick inverse tangent of opposite over adjacent. And then you would just say, okay, well then when x is 2, adjacent is 2, and you could type that in your calculator. And if you type that in, you should get 71.565 degrees. But because we didn't know the hypotenuse, you shouldn't be using sine or cosine. We should still be using tangent. And then you can just type that in. So here it's one where you got to break it up. So this is one where it's just one angle. You're just using inverse tangent, getting your answer. When it's like two angles like this that make up a bigger right angle, right triangle angle, that's when you got to do the setup. The big inverse tangent minus the little inverse tangent equals this leftover theta. So let's see how it's set up. It says, imagine you and your friends are going to drive a movie. The screen is 40 feet high and elevated height 60 feet on post. If you park your car 77 feet away from the screen, at what angle will you be watching the movie? So this is the movie screen, and you're here. So the angle that you're watching the movie is this top theta, which is not a right triangle. So we got to set it up how we set up the other ones before this. So the big angle is A, and we can see that if we were going to do opposite over adjacent, the opposite side for the big triangle would be this 60 plus 40, 100, and the adjacent side is X. So the first thing you're going to do is set up the A is inverse tangent of I said 100 over 77 because 100 is the opposite, and they said you're 77 feet away, so this X is 77. So that gets you alpha, and now we need this bottom one, which is phi. It doesn't matter what you want to call that, but this bottom angle, the opposite is 60, and the adjacent is still 77. So Wait, is it 66? Why do I have 66? It's 60. I don't know. Hold on. Okay. So you would do inverse tangent of 100 divided by 77 for the big angle, inverse tangent of 60 divided by 77 for the little angle, and then subtract them to get that top angle that was our viewing angle of the screen. And if you type that in the calculator, you should get 14.48. Now, I think that's correct. I think I just typed the 66 wrong. So hopefully you're starting to get the pattern. If not, let me know and we can meet on Google Meet and kind of break those down more if you're struggling with the real world problems. And here you can self-evaluate yourself. So here's a summary of just reviewing those. When you're using the unit circle, basically, you have those restrictions where you're only looking in two quadrants. Sine and tangent, you're looking in quadrant 1 and 4. Cosine, you're looking in quadrant 1 and 2. And then a summary video and a congratulations. So last thing I want to do is I put one more example that you might help you on a test problem when you go take that test for this unit. Is it says a ladder that's 13 feet long is leaning against a pillar. The vertical height from the base of the pillar to the top of the ladder is 12 feet. Which expression represents the angle theta that the bottom of the ladder makes with the ground? Okay, so for the test, there's a problem where it doesn't only want tangent. It wants all of them, sine, cosine, and tangent. So I wanted to show you because all of these in the tutorial use tangent, inverse tangent. So if you think about it, they give you two sides. We could go find the third side. Like even on those other problems, if we wanted to, we could have found the hypotenuse using Pythagorean theorem. We just didn't need to because we could use tangent. But here, if we're going to find all three, we're going to need all three sides. So here's a picture to help you. They said the ladder's 13. So if it's leaning against a wall, that's your hypotenuse, right? And then the vertical height is 12. So then we're missing this bottom length of the base of the ladder to the base of the wall. So if we plug in 13 to Pythagorean theorem for the hypotenuse, which is C, and we plug in 12 for A or B, and then we solve for the other leg, which I just made X, but you could leave it A or B, you should get 5. So now we know this ground length is 5. So now we could set up, think about this is theta, the angle the ladder makes with the ground. So let's go through all of them. So sine, theta would equal inverse sine, which is sine is opposite over hypotenuse. So the opposite wall side is 12 and the hypotenuse is 13. So if you took inverse sine of 12 over 13, that would be theta. Or if we wanted to find theta in terms of cosine, we could do inverse cosine of adjacent over hypotenuse. Well, the adjacent leg is 5 and the hypotenuse is 13. Or you could do inverse tangent of opposite over adjacent, which would be 12 over 5. So if you type all those in the calculator, you should get the same answer. It's just 3 different ways to find that angle. Okay. So I think that's all I have. It's pretty straightforward, the test. If there's anything that comes up as throughout the week, I can make an additional video or write out an example. So just be on the lookout for that. Be on the lookout for that and just communicate if you have any issues, because I can always create more examples or we can go over some together. So be expecting probably on Wednesday around 1 p.m. If you need to join a Google Meet for questions, that will be available. But other than that, I think that's it. So if you need anything else as you're working, just let me know. I'm here to help y'all. Y'all have a good rest of your day.